No, it certainly does not matter whether you're ready for this or not. So we're going to continue with lecture 7 and then kind of go right into lecture 8 from here, and we'll see how much we can get through today. So we were talking about regressions. We're talking about linear regressions and how we can fit, basically take a set of data, be able to fit kind of a model to it, and then apply that model to other data to hopefully have some predictive ability when we're looking at various variables. Now we're going to be looking at comparing models here. So comparing models is going to be one of the major parts of statistics. So and you can always add in more parameters. We'll talk about multivariable regressions that allow you to look at multiple variables and its effect on a specific predictor. But it doesn't just mean because you have a model that explains every component of that. There's always other things that you may not have taken into account that could be going on within a population. So, and again, if you are basically looking at a model, if it has too few parameters, it's really not going to be able to fit the data well. And remember we talked about that R-squared value kind of telling us what percentage of the scatter that we can see there, or what percentage of the variability is being due to our parameters that we selected. So obviously a higher R-squared value is going to be better because that has more kind of predictive value, more of that Y value is kind of being predicted from the X. If you have too many parameters, you're going to see that at a certain point the confidence intervals are going to be so wide that it's very difficult to be able to kind of make very accurate estimates, because you remember as you start to include more variables, your confidence intervals widen out, and then anywhere that range of that actual best fit line could actually sit, you're 95% sure it's in there, but if it's not super exact, if it's very wide, it's hard to make accurate predictions based on that. So if you were to look at a linear regression as a comparison of models, you can see here that frequently your null hypothesis is going to be that line is basically flat, or that your R-squared would be 0 at that point. There's basically no predictive ability here, and that in order to reject that null hypothesis, you would show that your linear regression line has a significance, is statistically significant to fit that data better than that null hypothesis. So when we're looking at models, it's oftentimes what we're rejecting is that if the p-value is less than our alpha, usually 0.05, that we can reject that null hypothesis and say that this best fit line does fit the data better than just a flat line. So again, the meaning of R-squared, that linear model regression fits the data better, and then it will have less variability of the points around the null hypothesis in that horizontal line. So if you were to measure the distance between all of those points to the horizontal line, that sum would end up being bigger than it would be if you were to measure the distance between the best fit line and those data points, right? So that's the idea, is that the best fit line, because it has kind of shorter distances between the data points and the actual line itself. So just looking at here, this is kind of some of the way they will compute how well the best fit line fits the data versus the null hypothesis, and will allow you to come up with that R-squared value, and will also end up coming up with eventually a p-value that will allow you to be able to reject that null hypothesis. And so in this case, we saw before that your R-squared ended up being 0.593, which means that basically around 59% of the variability is being accounted for by that X variable in the ability to predict a Y. Everything else is either due to biological differences or some other factors that we may not have fit into this. And keep in mind, this is only with doing a linear regression. We're only looking at one variable predicting one other thing. So how well we can predict Y from the X variable. So we can also do nonlinear regressions, and so as you might imagine, with linear regressions, it's just a straight line. These are going to be not straight lines. So you'll also see curves for these. So you'll see that nonlinear regressions are going to be more general than your linear regressions. They're going to fit the data much better, but they're we'll see some of the limitations with them. And basically, they're much more computationally intensive than what we saw with linear regression. Like with that, it was just a simple equation of a line, y equals mx plus b. But here you're going to be seeing that the curve that fits that is going to require a lot of calculus and other types of math in order to actually get a best fit line there. You couldn't just do it by hand. So again, the goal with nonlinear regression is to find the best curve that's going to come closest to the data. And you may see it used in lots of different fields of science. So again, we're going to look back at the rat data where they're looking at the bladder muscle relaxation in the presence of norepinephrine. Remember that the x-axis is going to be logarithmic, so this is going to be the x-axis being the norepinephrine concentration, and then we're going to be looking at the bladder muscle relaxation on the y-axis. So being able to predict how much relaxation you're going to get based on the concentration of the norepinephrine that you're going to be administering there. So again, the first thing you're going to do is choose a model and then decide which of the parameters in the model should really fit the data and which ones needs to be fixed at kind of constant values. So that's how we basically decided that if you have no norepinephrine being administered, you should basically have that muscle relaxation. That should be your 0 point. That should be kind of your baseline. And anything above that, as you increase the norepinephrine concentration, should increase the relaxation there. And again, this is all calculated usually by your stats programs. So again, here's just the data. We'll see the line that's going to be fit to this. Again, the norepinephrine concentration is going to be in a log scale, so we'll see that in just a second. So you notice here that the distance between the data points and the line itself is much, much shorter than you saw with linear regression, right? Because we can generate a curve that's a very intensive mathematical calculation or equation that's going to be able to fit that data much, much better. So if you imagine, is your R square valued for a curve like this larger or smaller than those linear regressions we were looking at previously? Probably a lot bigger, right? You're probably close to 100% of that variability being predicted based on that curve, right? We'll see how that bears out in just a minute. Again, so both linear and nonlinear regression are seeking to find the values of the parameters that make the model come as close as possible to the data, right? Because then you can take that model and apply it elsewhere to try to get some predictive ability. With the linear regression, you're going to see it's going to fit one simple model, can be explained by simple algebra, as we mentioned that the equation for a line. But with the nonlinear regression, it can really fit any model that you want. It's going to be much more kind of robust in the models that you can apply it to. And again, it's going to be using a lot of calculus and things like matrix algebra in order to come up with those equations. So let the computers do it for you. So at the results, if we're looking at this, again, the whole point is to fit that curve to the data, and you notice that the values or the curve is much closer to the data points than what you see with a linear regression. And so typically you're going to be interpreting these results in kind of a more scientific context, and what you can do is kind of look at kind of the midpoint, kind of the EC 50 or that effective concentration 50. And so if you were to look at the concentration of norepinephrine you need to hit to cause basically 50% of the maximal muscle relaxation, it basically came out to be 2.3 micromolar concentration in order to get that. And so that, based on that value, that EC50 or that 50% mark on the curve, that's where you would generate your 95% confidence interval around it and get your p-value from. So again, and then looking at the actual confidence interval around that, you would see that it's anywhere between 1.75 to 3.02 micromolar. Very, very small, very narrow confidence interval, because we saw how well that data is being fit to that line. So again, you get very narrow confidence intervals when you're doing that. So again, looking at the R squared value, again, looking at the fraction of the total variance of y that is explained by the model, you see here that the R squared value is 0.997. So that means that a lot of the values of y can be predicted from x very accurately, because most of the variance is being explained by that model. So again, nonlinear regression, you can typically get much larger R squared values. It's just more difficult to come up with those curves. So some of the assumptions that you're making when you're performing a nonlinear regression: one, hopefully your model is correct. Again, the computer's doing all the math for you. Hopefully that should be the case. The independent variable really has no variability. So in that case, when we were looking at the norepinephrine concentrations and the muscle relaxation, which one was our independent variable?
The norepinephrine level?
Yeah, because that's the thing we're changing, right? Because we can modify the norepinephrine concentrations and then experimentally see what the bladder muscle relaxation was. So that would be our independent variable. There's really no variability in that, because again, we're the ones applying the norepinephrine in that case. We know exactly what the values are for that. The scatter of the data should be Gaussian in nature. So again, you can do tests to run for that. And then the variability around the curve should be the same throughout. So there shouldn't really be much change in variability throughout that. Again, the data points are going to be independent of one another, and then the value of x is not used to compute y. So you see a lot of these assumptions that were used in linear regressions are going to pop up here in nonlinear regressions as well. Okay, so some other varieties you might see being used. We'll talk about multiple, logistic, and proportional hazard regressions. Okay, so the goal of looking at a multivariable regression, if I say multivariable regression, what do you think that means? Multiple variables, right? So instead of just using something like linear regression, we're using one variable to predict one outcome. We're going to use potentially multiple variables in order to try to see what their effects on a particular outcome is. And so, again, in a laboratory experiment, it's nice because you can control all the variables, like in that rat study. Usually, though, in the real world, you don't really have as much control as you'd probably like. But in this case, in a laboratory experiment, you can change one variable. You can measure another and then analyze the data with some statistic tests you can run on that. And so, again, very frequently you want to be able to look to see how one variable is being affected by multiple other ones. So, for instance, we're going to look at something like lead concentration on decline in renal function, right? And so, certainly, lead concentration can have a negative effect on renal function. But what are some other things that can have an effect on renal function? Drugs, disease states, age, all this, so lots of other variables that we can take into account to see how they're affecting change in renal function, and not just lead concentration. So again, being able to use these regressions to see how each one of those variables is having an effect on our outcome. So again, in some kind of experiments and most observational studies, the outcome you measure can be affected by multiple other variables, as we just mentioned. And so using multiple variable methods are pretty powerful, pretty versatile, and widely used. So you'll see it come up in the medical literature with some frequency. So here we're just going to introduce kind of the basic concepts and a few varieties of them. Essentially, what we're going to be doing is multiple regression methods are used for several purposes. Here, they can assess the impact of one variable while adjusting for the others. So basically what you can say is, even though you're looking at patients who may have different disease states or different ages and things like that, you can control for each one of those factors and see how, when you control for those, how the one independent variable that you're looking at, when you change that, how it has that effect on that outcome, right? So you can control for those differences there between your patients. And again, you can use this to create an equation for making useful predictions. So again, taking that model that you're forming and being able to generalize it and apply it to other patients, not just the ones you studied. And then potentially how you can understand scientifically how various variables might have an impact on your outcome. So some of the lingo we'll see, so there's multiple forms of different kinds of multiple regression. So again, there's lots of different varieties, there's a whole family of them, but we'll all kind of fall under this umbrella of multiple regressions. And then obviously the variables are going to be the things that are kind of our predictors. So our outcome variable is going to be y, and then all the different predictor variables are going to be x's that we can try to change and modify and control for. So those will be our independent variables. The y is always going to be our dependent variable in that situation. And then you'll frequently hear the term multivariate, which is probably used kind of inconsistently. When we're saying multivariable, that's meaning to use multiple x predictors in order to determine y. That's multivariable. Multivariate would be if you had multiple outcomes. So you have multiple different y's that you're trying to predict for. So just keep in mind there's a little bit different distinction there. You may hear the terms used incorrectly. So this is a 1992 study where they were looking at does lead account for decreased kidney function with age. And so we'll just use as one of our assumptions that if you have increased lead levels, that you would see a decline in kidney function over time. And so basically, they want to see what that actual interaction was when they studied this. And so again, they knew lead decreases kidney function. They also knew that kidney function decreases with age, as we kind of mentioned previously, and that typically most people can accumulate small amounts of lead as they get older, just due to natural exposure to the metal. Naturally will accumulate some throughout your life. And so they wanted to know whether or not this accumulation of lead could explain some of the decrease in kidney function that you see along with aging, right? So perhaps it's just aging causing the decline in kidney function, or is this somewhat this accumulation of lead having an impact as well? So that's one of the things that we're looking at. So this is just looking at the male data. There was female data as well, but this for this example, just kind of peeling out that particular data. And so what they did was they were measuring serum lead concentrations, and they were also looking at creatinine clearance as well. GFR usually That's how they're measuring that. And so, again, the subjects with more lead tended to have a lower creatinine clearance. That was one of the observations they made in that study. And again, that wasn't a totally useful finding in and of itself, because we also knew that, lead increases with age, and creatinine clearance is going to be decreasing anyway with age as well. So they wanted to get a better idea of what that actual effect of the increasing lead concentrations was on that. So again, they were considering in this case that the difference in age is really confounding your data there, right? So again, confounders is going to be anything that is skewing your data somewhat, or something you need to control for that could be having an impact on your data, right? So in this case, the change in age is confounding the data. We want to find out specifically what the lead is doing to these patients' creatinine clearance. Does that make sense? So again, if you ever hear, we controlled for these confounders, that's really what they're saying, is that they're trying to take the impact of those variables out of the equation, so that way you can look at the things, the outcomes that you're really interested in. So very frequently, age is something that they'll take into account. You may look at gender, you may look at disease states. Those are all common confounders you'll see being controlled for frequently. So to adjust for the confounders, the investigators used multiple regression to adjust for age and for some other factors. So we'll look at what those are in just a minute. And then the X variable that we're going to be using for the graphs you'll see are going to be the log of the lead concentration. The reason why we're using the log is because the concentrations are independent and multiplicative, so we had to convert it over to a log so that the data would kind of make more sense. And then our Y variable, our dependent variable, is going to be that creatinine clearance we mentioned. So here what we're going to be seeing is that the model that we're using is predicting the value from the baseline value plus the effects of 5 independent variables, each multiplied by a parameter. So we'll see what that table looks like, and those other factors that we're going to be looking at are going to be for this particular instance. So here, they were basically using the term beta, or the figure beta, in order to reference these different parameters they're going to be looking at. And so you can see they're looking at the serum lead concentration, using the log of that. Notice they're using age, body mass, using GGT. Had the patients ever been exposed to a diuretic? And so when you're looking at that, what do you notice about the units between those different parameters? Yeah, they're not going to match. And is that okay? Yes, we can actually control for that. So just because, if you look at diuretics, whether that's a yes or no, that's what kind of type of variable? So it's kind of like a yes-no variable. It's a dichotomous variable. It's a nominal variable, right? So it's really it's either kind of a 1 or 0 in a lot of those cases. But then you have things like age, which is obviously measured in years. Lead concentrations probably in micrograms per ml, something like that. Body mass in kilograms. So you can have different units being used here. And even though that your outcome variable is creatinine clearance, which is usually mLs per minute, that's okay. You can use you can kind of control for those differences there. But in this case, what they were doing is they were controlling for these different confounders and basically taking the impact of those different variables out of the equation, so that way you could just look specifically at lead concentration and how that predicted how increasing levels of that changed the creatinine clearance, right? So basically just trying to control for that so you can get a better idea of specifically what's going on between that interaction of lead and creatinine clearance. So again, just notice here that they are the different units that they're using. Frequently for those dichotomous variables, they either use 0 or 1. So 0 being no exposure, 1 being exposure, and it's okay that these are all different units. So when you do the multiple regression, we're fitting the model to the data they had in those 900 some odd patients, and then getting the values, so those coefficients, to make it so that the model comes as close as possible to predicting the actual data. So basically they're getting that best fit line that they can determine based on the data that they're seeing here. And if you had to imagine the effect that increasing lead concentrations has on creatinine clearance, what do you think that R value is going to look like? Should it be positive or should it be negative? Yeah, it should be negative, right? Because as lead levels go up, you would think that creatinine clearance is going to go down. So because those are inversely proportional, you expect that R value to be negative, right? Because it's going to be a downward trending line. If you looked at the R squared value, should that be positive or negative? Should always be positive, right? Yeah, because it's squared. So anytime you're squaring a number, whether it's positive or negative, it should be positive after that. So it's going to be somewhere between 0 and 1 in that case. So again, we're looking for that best fit line along with a confidence interval to kind of give us a range for what we can see there. And so, and then you get one p-values being reported for that to say whether or not that a flat line or having an R squared of 0 is your null hypothesis saying that the change in lead concentrations has no effect whatsoever in changing creatinine clearance, versus our hypothesis being that we can reject that and say that yes, increasing lead concentrations will decrease kidney function, but by how much is what we want to find out, right? So again, you're doing multiple linear regression models that do not distinguish between the X variables that you really care about, so you're kind of just adjusting for them. And again, the statistics programs are kind of doing that for you, where they're taking the impact of those different variables out and kind of controlling for them. So you're kind of working on an even playing field, even though you have patients with different factors. You know, some have diuretics, some are older. You can take those impacts out of that and control for all of those. So, and again, after adjusting for all those effects of the other variables, they wanted to see is there a substantial linear relationship between logarithm of the lead concentration and the creatinine clearance, right? And keep in mind, you could do this with any of the variables. So say if you wanted to look at specifically body mass instead, you can control for the lead concentration at that point and all the other variables, and then look at the body mass and then compare that to the creatinine clearance, right? So those are things you can do as well. You can change what your X variable that you're really concerned with at that point. So in this instance, and just note that green line, I actually, the information that I had on there was probably incorrect, so I actually went back to the study itself and pulled that information, so you can change your numbers back to that. But essentially what they found was that for the best fit line for that lead concentration was basically a negative 9.5 mLs per minute. So essentially what they were saying is that as you increase the lead concentrations by 1 unit, basically you were seeing a decline in kidney function by about 9.5 mLs per minute, right? So that makes sense. We said that R value is going to be negative because, again, we were saying that by increasing lead concentrations, we would assume that kidney function would go down along with that. So here you would see that you'd have a 95% confidence interval that's being calculated here, and you see that would range anywhere between negative 13.9 mLs per minute to negative 5.1 mLs per minute. And so based on that, would you think that that would be clinically significant? You think so? Okay. Why do you think so? Yeah, so it doesn't cross 0 in this case. So right, so again, when we were looking at this, you know, if, there's a potential that the values could have gone up. Maybe someone had increased kidney function with increased lead concentrations that was skewing the data. So if the 95% confidence interval in this case were to cross 0, that would mean that the results would be non-significant, right? But because they don't, because they're staying consistently negative, do not include 0, we can conclude that this is going to be statistically significant. So basically what they're saying, the results is that a 10-fold increase in lead concentration would reduce kidney function by around 10% or so. And based on that, the confidence interval would range anywhere between 1 to 20% as you increase those levels. So here's a graph kind of showing that, and you can see that as you're increasing the log of the lead concentration, you're seeing that the range there is kind of going up. So again, the scale is going to look a little bit different than what your normal linear regression would look like, but that's only because we're looking at the logarithmic of that lead concentration there. But you can kind of see the confidence intervals and how those kind of range with the lead concentration. Again, you know, the R value is negative because it's going down. Okay. So again, here, even though the authors do not quantify that the p-value is less than 0.05, because we know that we can interpret those confidence intervals, that we can say that yes, this is going to be statistically significant. We know it's less than 0.05 based on this. So then using that information, you can take that data and kind of go back and look at say a person's lead concentration and kind of assume kind of what kind of decline in kidney function they might be having on that. So you can predict that in other male patients, presumably, when looking at those lead concentrations. Okay, so again, when we did the multiple regression, it actually reported out you had an R squared value that equal 0.27. So what does that tell you? Well, basically, it's only that about 27% of the variability in that creatinine clearance was really being explained by that particular model, and that 73% of that variation could be due to other factors, right? So it could be random sampling, could be biological differences. And again, there's no way to really have the perfect best fit line. There's oftentimes too many independent variables that can be affecting creatinine clearance, right? So again, we can know that lead has some impact on this. Around 27% of that variability can be accounted for by that. But obviously, there's other factors out there that are influencing that as well. So keep in mind that there's still lots of other factors that can impact this, and that a low R squared value is not necessarily inherently not useful, but it's just keep in mind what they're testing and what they're actually looking at and what could be also influencing this. So here, so in this book, the person was basically taking that data and looking at, basically kind of recreated the data itself, and they were looking at the best fit line for that. And so you can see here just kind of a representation of what that R-squared value kind of looks like. Even though the data is still pretty scattered around that, it still fits that trend. And again, about 27% of that can be accounted for by that change in lead concentration. Okay, so again, when looking at this stuff, usually with an observational study, like looking at lead concentrations and creatinine clearances in this population, you didn't really do an intervention. You're just kind of looking at the data that's present and kind of just making some inferences about that. So it really doesn't prove cause and effect in a lot of cases, but it could provide potential, hypothesis generation for future studies, right? So to really get a good cause and effect relationship, you need to do prospective studies. And so very frequently, you'll see observational studies being done or retrospectives being done to give you an idea of possibly what's going on, to generate some ideas, and then ideally you'd want to produce a prospective study that looks specifically at this. It can kind of tell you more whether or not there's a cause and effect relationship here, right? So just remember that anytime you're looking at an observational study, retrospective study, there's only so much credence you can take from any kind of cause and effect relationship. You really need to do prospective studies to show you that. Okay. So we can continue on. Another variety is going to be logistic regression. And so this is going to be used when there's two possible outcomes. And so the study they're using as an example here was basically they created a model that was predicting the prevalence of obesity in Iranian women. And so again, the outcome, our Y variable here in this case, would be obesity. So that's either yes or no. So again, it's one of those kind of nominal dichotomous variables here. And then they want to create a model that predicted the prevalence of obesity as a function of various demographic variables. They were looking at different factors like where do they live, did they smoke, what kind of education did they have, and looking to see what kind of influence that had on the rate of obesity. So they were looking at three independent variables, one of which was going to be age and number of years of education. So again, those are going to be continuous variables. You can see also that they can use things like binary variables like smoking status, marital status, place of residence, whether it's urban or not. So again, you can use multiple types of variables here when you're doing these logistic regressions. And then they can also use economic indexes. So it had four categories here. So it's kind of an assigned binary variables that they were coming up with. So their N value, they were looking at 14,000 Iranian women here, and then they used the logarithms to form these odds ratios. And again, you guys remember we talked about odds ratios yesterday, basically just the odds of something happening versus it not happening. Or so in this case, the odds of someone being obese versus not being obese. Again, when you're looking at cohort studies, odds ratios are going to be the way to go for this. And in this case, with the logistic regression, you're generating odds ratios for this as well. Okay, so here we're going to see that when looking at all the different variables, there are 8 independent variables that we're looking at, and so that'll generate odds ratios for each one of those. You can see how that'll have an impact on the values. And so the idea here is that if we take the particular x value, whatever that independent variable is, one of those 8, and we increased it by 1 while keeping all of the other variables the same, how much would the logarithm of the odds ratio be expected to increase, or how much would that increase our odds of a woman being obese? Okay, so again, you're still controlling for all the other variables when you're looking at each one of these individually, so you try to take the effect out of those and kind of look at it at an even playing field, so you're only really assessing that one independent variable. So again, if the odds ratio is near 1, because again it's a ratio, if it crosses 1, we know that the result is going to be not significant, and we know that that particular variable is going to have little impact on whether these women are going to be obese or not. If the odds ratio is going to be much higher than 1, what do you think that tells you? Yeah, so it increases your odds for obesity, and then if it's much less than 1, it would be more, your odds of being obese are much less likely, right? So then, based on that, we're going to look at these different odds ratios and see what kind of effects we can kind of gather from this. So the first one we'll see is looking at the idea of whether they're living in an urban environment or not. So I guess more of a rural environment. And so based on that, you see the odds ratio is 2.13. So what do you think that means to you guys? So it's higher. So they're 2 times as likely to develop obesity, right? If you're living in an urban environment. Okay, and so then you got to look at the confidence interval to determine whether or not that's going to be significant. So in this case, it ranged from say 1.915 to 2.369. Is that significant? Yeah, it is, because again, it does not cross 1. Because again, 1 is our baseline odds, right? So if we're greater than 1, we know that the odds of obesity are going to be more likely. And in this case, because the confidence interval does not cross 1, we know that yes, when controlling for all these other independent variables and just looking at whether these women are living in an urban or non-urban environment, we see that they're about 2 times the odds of developing obesity if they are living in an urban environment. Okay. And so this is again where you kind of generate the data, and then in your summary section or your discussion section of the article, you can talk more about why you think that is, right? And why you may want to investigate a particular aspect of their life after this, maybe dig deeper into why the urban environment was more predisposed to developing obesity. So anyway, going down and looking at age, so you see the odds ratio is 1.02. What do you think that means?
Even, right?
Yeah, it's pretty much about the same. Maybe only like a 2% increase in odds of having obesity. So really nothing too spectacular there, though. But what do you think about the confidence interval? Is that significant? Yeah, it's pretty narrow, but is it significant or not? Yeah, because it doesn't cross 1. So we know that age does have an influence on whether or not these patients or these women are obese or not. But what is that actual impact? Is that clinically significant? No, right? So that's the thing. Even though it's statistically significant, we can prove that by looking at the confidence intervals. We still see that has a very, very small impact on that. So you'd be better off looking at something like the urban setting versus looking at the age and causing obesity in these women, right? Because again, clinically, it's not all that too interesting. Then looking at education. So what do you think when you're looking at the education aspect? So is that increasing their odds or decreasing their odds of obesity? Yeah, so you decrease about 2% less odds of them developing obesity, and is that statistically significant? Yes, it is statistically significant, right? Because it doesn't cross 1 in this case. So even though it's statistically significant, again, is it clinically significant?
No.
Probably not, right? Just a 2% reduction, probably not such a big deal, right? So education is not a big deal. How about looking at smoking? Yeah, so it's a pretty decent decrease there. So around 35% drop in their odds of developing obesity, and then that would also be statistically significant. So that might be one you actually want to look at, right? Because your odds can't go below 0, but by having a 35% decrease in that, that might be something worth investigating, right? So looking at smoking and the effects on weight hazards there, because we typically know that smoking does what to your weight? Typically decreases it. Yeah.
Is that what that's saying? Like if they said yes to smoking, then there would be almost like a 35% decrease.
Yeah, decreasing the odds of them being obese. Okay. Yeah. Essentially, that's what that's saying. And then looking at being married, I can probably attest to this to some degree. That appears to be,
Careful.
Yeah. So being married tend to have increased odds of these women being obese, and again, that would be statistically significant. Is there anything on there you see to not be statistically significant?
Nothing crosses 1.
Yeah, I don't see really anything else either, right? So everything else looks to be statistically significant. And if you again look at the number of patients that we're looking at 14,000 women. That's a huge patient population. So being able to do kind of those observational studies where you can use a ton of data, you notice that your confidence intervals tend to be really, really small, and you can achieve that statistical significance much more easily, right? So you're less likely to make a type 1 error as your population size goes up.
How come the confidence interval for the higher class goes from 1.9 to 1.4? Like why does it?
Why does it go down?
Why
For
does
which
it
one?
go down?
That was probably an error in reporting that. I would assume they were dyslexic that day and probably got it backwards. Yeah, I don't know. I'd have to guess that's probably what it is. Otherwise, you have to go back in the study and actually find what they did. And again, that's why you should always be careful when you're looking at like summaries of studies and things like that. You always want to go back to the actual article and make sure that the data actually matches up to what you're being reported.
The odds ratio, is it somewhere in the mean of the confidence interval? Is that? I mean, I'm just making an observation from what I'm looking at here. I missed yesterday, but is it going to fall in that confidence interval?
Generally, yes. So again, that last one, the higher class might be kind of goofing it up a little bit there.
But
Yep.
all the others seem to fall somewhere near the mean, I would think, of that confidence interval.
Yeah, so generally those confidence intervals should be centered around that odds ratio.
Okay.
Yeah. And so one of the things they mentioned on the last slide is that when you're looking at just specific odds ratios, it's potential to have asymmetric confidence intervals. When they do the log of it, it ends up becoming symmetrical. So that's why you normally see that.
Thank you.
Yep. So anyway, so kind of what we were already saying there. So again, if you're looking at patients who are living in the city, you saw a corresponding odds ratio of 2.13. So again, twice the odds, those women being obese in that situation. So and again, we know the confidence interval is telling us it's significant because it does not cross 1. So all of which we've kind of already said. Okay. Another thing that you could do other than logistic regression, you could do a proportional hazard regression. And so this is something that's kind of similar to those survival curves that we looked at, those Kaplan-Meier curves. And so essentially this is going to be used when an outcome is elapsed, basically it's an elapsed time to an event. You can use it for survival, you can use it for different events as long as they have a very clear defined time frame. So if you're looking at something like children having febrile seizures, so you can look specifically at the study in 93 where they were looking at diazepam. It's a benzodiazepine we'll talk more about in Pharm 2, whether or not that would prevent febrile seizures in children. And so basically what they're doing is they had 400 children who had a history of at least one febrile seizure in their past, and then they were instructed to either to medicate the child when they had a fever. And so basically they had children who were either in the treatment group where they got diazepam, and they had children in the placebo group who got nothing. And so basically they're comparing the time or until patients had a seizure or that they actually developed a seizure in those cases. So by comparing the two groups, you can see whether there was a difference in the time until the first seizure. So again, this is just a method used to analyze data through a survival analysis, but keep in mind death is not always using those survival analyses. It's just really something that has a clear-cut endpoint you can measure time until, right? So you can use it to something like seizures, you can do it to disease progression, you can do it to any kind of type of variable as long as it has a defined time frame. And again, here when they were looking at these kids, you want to adjust for things like differences in age, number of previous febrile seizures, and other variables as well in order to make sure you're taking out the those confounders and making sure that the data you're looking at is really just looking at the outcomes that you're interested in. So again, when you're looking at the survival curve plots, it's looking at cumulative survival as a function of time. So that slope is basically the rate of whatever your event is that's happening here. So in this case, it would be the rate of those febrile seizures occurring in those patients who either received diazepam or didn't. It could be rate of dying in a short time interval, which can be frequently termed as hazard as well. So that's where the hazard model comes from. So in this case, if you had 20% of patients with a certain disease are expected to die this year, the hazard would end up being something like 20% per year. Okay, that's where the term hazard is coming from. And then when comparing the two groups, it's assumed that the ratio of hazard functions is consistent over time and that they're proportional. So that way, the risk of death or the risk of your event does not change over time. It should be pretty much consistent throughout. So that's one of the assumptions you're making when you do that. And then when you're comparing those hazards to one another, essentially what you're getting is a relative risk. Right, so we talked about that previously. I think yesterday we talked about that. And so again, the assumptions may not always be reasonable in some cases, and so you have to really look at the model that they're using kind of carefully. But essentially, this is very similar to a logistic regression, but you're going to end up getting relative risk values spit out instead of odds ratios. So again, a little bit different in how we're going to be doing that. And that kind of makes sense because in a lot of those logistic regression scenarios, you're using kind of data that was already collected, right? This kind of retrospective data. And so you're looking at the prevalence of obesity, and you're looking at the prevalence of those women who had education, higher education, or they smoked and things like that. So you want to look at odds ratios versus here, if we're looking at survival times, this is going to be more of a prospective in nature, and so you can get relative risk because you're looking at the incidence of new events occurring as time goes on. So in this case, what we found was the relative risk ended up being 0.61 in the diazepam group. So what do you think that means? So diazepam effective in preventing febrile seizures? Yeah, so it's less than 1, right? Because we're doing a relative risk, so we're doing a proportion of risk to one another. So because it's less than 1, we would say yes, those patients in the diazepam group had a lower risk of developing a febrile seizure. And you can look at the confidence interval there, ranges between 0.39 to 0.94. Because that does not include 1, right? Because it's a proportion. Then we would say that yes, that would be significant. And here you can see the p-value is 0.027. So again, compared to the placebo group, subjects in the treatment group had only 61% risk of having a febrile seizure, and then basically at that point you can reject the null hypothesis that saying that there's no difference in the incidence of febrile seizures in patients getting diazepam versus not. Now, of course, that was a study done back in '93, and nowadays we don't really do prophylaxis. We don't really give seizure meds typically to febrile seizures, but you'll learn about that in neurology. So again, assumptions you should be making when trying to run these type of models is that one, you're doing random sampling from a population, and that you're going to have these linear effects with no interaction beyond what's really specified in the model. So again, by increasing the variable, the x variable by 1, should increase or decrease the value of y. In the case when we were doing a multiple regression, that's what you're going to be looking at. Or if you're doing logistic regression, you're looking at the log of the odds ratio being affected that way. And then if you're doing the hazard ratio, you're looking at the relative risk, right? So they should all be changing by the same amount as you change the x value, right? So if I change it by 1, whatever change in y I get should be proportional throughout the entire range of changes in x. Again, they should be independent observations, and that the random component of the model should be correct, so that we're measuring things like the seizure correctly, that we're measuring whatever it is that the data points that we're collecting. All those should be accurate. And again, if you're looking at the linear regression, you're assuming that the distribution of the data is normal. You're looking at Gaussian distributions, and that hopefully the standard deviation or the scatter is going to be the same throughout the range of data. So it's kind of the assumptions you're making when you're performing these. And then for logistic regression, because you're looking at kind of yes/no kind of dichotomous variables here, the two outcomes should really follow binomial distribution. Okay. So going into the questions and answers for this section. So do the x and y values have to have the same units to perform a linear regression? No, right? So we said that they can have different variables, different units. We said that especially when you're doing like multivariable regressions, you can have certainly different units there. It's no problem. Can linear regression work when all the x values are the same? So you collected a bunch of data and every single x value was the same. No, right? Because then even if your y value is changing, you can't really predict anything, right? You're not really going to get a best fit line based on that. How about when all the y values are the same? No, right? Because then there's nothing you're really predicting because y never changes, right? So you just say y is y. And then will the regression line be the same if you exchange x and y? Yeah, so remember when we're doing linear regression, you cannot change the x and y variable because what you're trying to do is trying to interpret, you're trying to say what best predicts y from x. If you try to flip that, then all of a sudden your thing's going to be changing unless the values were exactly the same and causing basically a straight line. The correlation, yeah. So if you're doing correlation, you can flip it. It's not really a big deal from that standpoint because you're not really predicting anything in that situation. You're just seeing how those two variables will kind of vary together as you increase or decrease them. So again, just like we kind of said here, specifically for that last one. So again, linear regression fits a model that best predicts y from x. If you swap the definitions, the regression line will be different unless the data points just happen to line up perfectly so that every point would actually be on that line. But we know very rarely that would ever be the case. Okay. Do you always have to decide which variable is the outcome dependent variable and the predictor is independent at the time of data collection? So you normally think so because again, you say you typically want to have go into an experiment having as much idea of what you want to be looking at as possible. But in this instance, when you're doing analyses like these, you can control for multiple different types of variables. So in which case, you can look at things like if you're going back to that creatinine clearance and the lead concentration data, if you're like, okay, well, the lead concentration didn't really show me anything, maybe I can look at something like body mass and see how that affects creatinine clearance, or I can look at the age or whatever happens to be. So you can kind of change those around a little bit. You want to be careful though if you kind of just go through the gamut until you find something that works, because then you're kind of biasing your data a little bit to try to make it look a little better than it probably does. So does it make sense to compare the value of one best fit parameter with another? Let's see what they say about that. So, in this case, no, the units of each parameter are going to be different, so you can't be directly compared. There's going to be some advanced methods of standardization we're not going to talk about here, so just be careful when they're directly comparing different parameters on a best fit line and trying to compare them to one another. So just be aware that there's different lines, hard to compare very easily. And then do all the independent variables have to be expressed in the same units? We already said no, they don't have to be. You can do those in different units, and that's perfectly fine. Okay, so any questions on that section? All right, I'm going to give you guys a 10-minute break. We'll come back and continue on with section 8. So we're going to do lecture 8 this time. This is actually a lie. This probably isn't the rest of statistics. There's actually more slides after this, but that's just the unfortunate name for it. But we'll see what's in here. So we're going to cover a few more tests that you can run that are important when looking at medical literature. One's going to be talking about ANOVAs. So you'll see them abbreviated as ANOVA. That's going to be referring to the analysis of variance. We'll talk about when to use those. We'll talk about multiple comparison tests that you're going to do after running ANOVAs. Then we're going to talk about some non-parametric tests, sensitivity, specificity, and receiver operator characteristic curves, or ROC curves. And we'll look at things like predictive values and some stuff with sample size and Bayesian statistics. So, yeah, I usually don't like to chat stats with my wife because I usually get in trouble as well. Anyway, yeah, I got her to move in with me. That's about as far as I can get with that. So the first thing we're going to talk about today is going to be analysis of variance, or ANOVAs. See this pop up pretty frequently in the medical literature. And so basically looking at the analysis of variance is a collection of statistical models in which the observed variance in a particular variable is partitioned into components attributable to different sources of variation. So simply what this means is that you're going to apply ANOVAs when you're testing for statistical significance between several groups that are all considered to be equal. So for instance, if you're looking at an unpaired t-test, how many groups are you looking at? How many groups are you comparing the means of? 2, right? If I'm doing an ANOVA, I'm going to do ANOVAs for anything greater than 2 groups, right? So this is basically if I have 3 groups, 4 groups, whatever happens to be, I can use an ANOVA for unpaired groups. Okay, so this is the alternative to a t-test, unpaired t-test, when you have multiple groups. And basically what this is saying is that, if I were to look at 3 different groups of patients and I was comparing a treatment between all 3 of them, and I compare A to B, and then A to C, and then B to C, what do I run into the problem of doing if I keep testing for statistical significance?
You'll find one.
Yeah, I'm going to find one, right? So it's I'm going to increase my chance of a type 1 error if I keep doing multiple comparisons. So we've talked about that previously. We know that's a problem. So what I can do with an ANOVA is I can run that for how many ever groups that I have that are normally distributed. So this is still a parametric test, and I can say that, okay, there's a difference somewhere in there. I can't say where. I just know that there's some difference between one of those groups to another. So instead of having to do a bunch of pairwise comparisons, I can just do one and say, okay, there's some difference there. Okay. Then the hard part comes when you have to start doing some tests after that in order to help figure something out. But again, they're very useful for doing multiple groups and just saying, okay, yes, there is some difference there. I just got to find where it is now. So the first type of ANOVA we'll talk about is a one-way ANOVA. It's going to be comparing the means of 3 or more groups, assuming that all the values are sampled from that Gaussian or normally distributed population, right? So as an example here, we're going to look at a study back in '93. They're interested in looking at hormonal changes in women. I don't know why this book focuses so much on the ladies. I guess we did the lead concentration with the guys, so I'm trying to get a little bit of gender equality there. Anywho, so they're looking at hormonal changes in women runners. So we know that, especially elite runners, they can certainly have some hormonal changes that can occur. And so what they're doing is they're actually measuring the level of luteinizing hormone in non-runners, recreational runners, and they were looking at elite runners. And of course, if you're looking at a study, they would have to identify what they meant by all of that. So how many miles per week they were running, or whatever happens to be. They should be explicit in saying how they define those different categories. And so they're doing a distribution of their hormone levels. It appeared to be log normal. So remember, we have to do, even though the data may not have looked like a normally distributed data, it ended up being log normal. So they just converted that concentration of luteinizing hormone to a log concentration. So then, they didn't publish the raw data, but they did publish a summary. And so we can use some information to look at the summary there. And basically, they're saying that, luteinizing hormone does not predict if someone is a runner, but they're looking to see how the changes, if you are a runner, how that can affect your luteinizing hormone. So what they ended up showing was the mean of non-runners. Basically, what their conclusion was that the mean of non-runners, based on the standard error of the mean bar, might be distinct from runners. So we're going to dive into those results and see if that's actually true or not. So when looking at these groups, you can see here the mean luteinizing hormone concentration. So you can see the log of the concentrations there, standard deviation, standard error of the mean, and then your N value for each one of those groups. And so you can see here that, just by looking at standard deviation bars and comparing those, just because they overlap, you can't really tell anything from that, right? So doesn't really tell you a whole lot. Now, on the other hand, we said that when you're comparing standard error of the mean bars, we said that if those do cross, what does that mean? It means it's very unlikely those results are going to have a p-value less than 0.05. So you can kind of already tell right off the bat that looking between elite runners and recreational runners, those standard error of the mean bars are, because again, those should be the smallest because they're going to be the ones that are divided by the square root of your N. So again, those are smaller than your standard deviation. So essentially, if they're crossing, that tells you that they're pretty close together and that there's no way that those values are statistically significant. So what the authors are saying is that there is a difference, though, between the elite runners and the non-runners. Okay, so that's basically what their conclusion was. We'll see if that actually bears out going forward. So again, if we were to do, what's the matter with doing multiple t-tests? We kind of already alluded to that. But if I did multiple unpaired t-tests, it would require comparisons between the non-runners and recreational runners and elite runners, and then non-runners and elite runners, right? So multiple comparisons there I'm making. And then you run into that problem where as I increase the number of comparisons I make, I'm just going to find something by random chance alone pretty easily. So, and then if the null was true, so we're saying the null hypothesis is true, what do you think the null hypothesis would have been in the study?
There's no difference between the groups.
Yeah, luteinizing hormone would be the same in all three groups of runners. It would not change whatsoever. So again, there's no difference between the three groups. If we say that, there would be a 5% chance that each t-test would yield at least a significant p-value, right? Unless you did some sort of correction, like you're doing like a Bonferroni correction or something like that. So with three or more comparisons, that chance that any one of them would be significantly higher than just looking at than your 5% value. So again, that's why I can't just do several t-tests in this example. So instead, what we can do is do a one-way ANOVA that will compare all the groups together at one time. So it'll tell us whether or not there's an actual difference there. So if you did a one-way ANOVA, it would give you a p-value that says 0.0039. And so what that result basically says is that, okay, well, we can reject the null hypothesis at that point that says there's no difference between any of the groups of runners, because now we have an ANOVA that's telling us, yes, there's a difference between one of the groups to one of the other ones, but ANOVA can only tell us so much. It tells us there's a difference there, but we don't know where. So at that point, when you're just doing this one test, because you're only doing one comparison, your p-value 0.05 still holds true, and you don't run into that multiple comparisons test. So in this case, the null hypothesis could be rejected. But again, clinically, it doesn't really tell you anything. As you say, okay, well, there's a difference in luteinizing hormone, but where's it at? That's what you want to find. So again, you're going to be basing your ANOVA assumptions on the same assumptions as an unpaired t-test. So again, the sample should be randomly selected, or at least representative of that population that you're sampling from. The observations within each were obtained independently. So again, you don't have people who can potentially fall into multiple categories and are being measured twice. And then the data you're sampling is going to be approximating a Gaussian distribution. So there are not really a lot of outliers that are fell within there. And then hopefully the standard deviation of all the population should be pretty much identical. They won't be exactly the same, but again, by including similar sample sizes, you can help to limit that standard deviation, hopefully get very similar values there. So the way that you can do a one-way ANOVA, and again, I'm not going to ask you how to calculate this specifically. I'd more ask you, what situations would you want to use a one-way ANOVA versus, say, an unpaired t-test or something like that. But just for your, just so you know how it's done, basically what they're doing is they're determining the sum of squares by fitting alternative models. So what that means is they're comparing three or more means with one-way ANOVAs that can be viewed as comparing the fit of the data to two models, essentially. So the null hypothesis would be that all the population share the same mean, and any difference is just due to random sampling. The alternative would be that all populations do not share the same mean. So that's really when you do a one-way ANOVA, that's what you're testing, to say like, okay, all three of these groups have the same mean versus they don't have the same mean. So Now, you can also have something called a repeated measures ANOVA. This is different than the one-way ANOVA. And essentially, this is what you would be, this is similar to the differences between an unpaired and a paired t-test, would be a one-way to a repeated measures ANOVA. So based on that, what do you think a repeated measures ANOVA would be used for? It's like paired groups, right? So it'd be, again, if you're doing repeated measures in the same person, if you had siblings or twins that were being used, laboratory experiments that were being run at the same time, or had several treatments being handled in parallel, again, you'd use a repeated measures ANOVA to do that. So again, if a test question came up and said, I'm comparing twins who are being given, 3 groups of twins. Say I was doing a triplet study and looking at changes in blood pressure or the exposure to whatever drug. What would be the best test to reject the null hypothesis that there's no difference between these groups? And you would say repeated measures ANOVA, because there's 3 groups and they are related to each other, or they're not independent. Okay. Because so again, if you want to do a one-way ANOVA, it would be for more than 2 groups, but there need to be independent samples, right? That's the big difference here. So repeated measures ANOVA is going to be for paired samples or not independent samples, similar to how a paired t-test is being used for that, paired data versus an unpaired t-test. So keep that distinction in mind and think to yourself, how many groups am I comparing, and then are these groups independent or not? And that'll usually get you 95% of the way. Yes?
So the purpose of these 2 tests is basically just to say there is a difference, we don't know what that difference is, and that's what
Exactly, because then after this, you're going to go into some further investigation. So this is very frequently done anytime you're comparing more than 2 groups in the medical literature. So it's very frequent you'll do this as an initial test, because again, if this tells you nothing, then you can say, yeah, I'm done. I don't have to do any more work here. I know there's no difference between these groups, right? But if I can reject that null hypothesis, now I can start to delve a little bit deeper, and then you can start to look at other multiple comparisons for things you're actually looking for. So we'll talk about that once we kind of get the baseline down. Yep. So again, using the repeated measures ANOVA is going to be for your paired groups, your non-independent groups. So you can certainly have some other varieties. So there's many other forms that can be used aside from just the one way. In our example, subjects were categorized in just one way and just by how much exercise they did. So you could also have multiple types of categorizations for those patients. So not just how much exercise they did, but if you're looking at the age of the women, if you're looking at other variables. And so this is when you can look at start looking at something like a two-way ANOVA. Okay, this is probably used less frequently, but again, it's something you still may run across when you're out there. So, for instance, if I was doing a two-way ANOVA, say I was looking at the exercise level for these women and their age, basically what this would do is actually compute for me 3 different p-values, right? Because I'm going to be testing 3 different null hypotheses at this point. The first one is going to be an interaction. So this is going to be a null hypothesis that there's no interaction between the 2 factors. That the fact that the differences in luteinizing hormone caused by exercise is going to be the same for all the age groups, right? So age group will have no effect on how luteinizing hormone is being affected by exercise. That's kind of the first p-value to get, the first null hypothesis. The next one you get would be for the first factor, and so the null that the population means are identical for each category of the first factor. So in this case, it would mean that the luteinizing hormone is the same for each level of exercise in the overall population, and that all the observed differences are just caused by chance alone. Okay? And then the second factor you get, or the third p-value you end up getting, would be the null is that the population means are identical for each category of the second factor. So in this case, it means that the mean luteinizing hormone is the same for all age groups in the overall population, and that all observed differences are caused by chance. Okay, so this is just getting things more complicated by including more variables in to your model here, and so you can find 3 p-values that tell you specifically what's going on here. If there is any differences between, say, the interaction between age and exercise, and then if exercise or age is having any effect on luteinizing hormone, or if it's all just due to random chance, right? So once you have your ANOVA results, say that the ANOVA came back and it was significant, showing us that yes, we know that exercise has some effect on luteinizing hormone. We just don't know which group we're actually seeing a difference in. This is where you start to do multiple comparison tests after the ANOVA. we said multiple comparison tests are a problem unless you're correcting for them, right? So we mentioned the Bonferroni correction is one way we can deal with multiple comparisons. How do you do a Bonferroni correction? You guys remember? It's in the video, but basically what you do is you're saying that if you do multiple comparisons, that you're using that level, that alpha level for the entire family of comparisons, right? So basically, if you're doing 6 comparisons, you would just take 0.05 divided by 6, and now every comparison that you're doing has to meet that p-value. Otherwise, it will not be considered statistically significant, right? So it's a pretty simple one, but it's a pretty easy one you can do. I certainly did Bonferroni corrections when doing my my study for coral snake research, the coral snake antivenom and treatment, because of the fact that I was doing a lot of comparisons between, intubation rates and looking at anaphylaxis and things like that. We did those Bonferroni corrections to make sure that we are not getting multiple comparisons issues, right? So your p-value drops that you have to meet because you're just dividing that alpha by all of the comparisons you're doing. So there's other methods you can do, and this is what we're going to look at when we look at multiple comparison tests being done after an ANOVA. So again, one way ANOVA is going to compute a single p-value that testing the null hypothesis that all the groups were sampled from populations with identical means. Okay, so if we can reject that, we know that there is some sort of difference in the means between the groups. And so these multiple comparison tests allow us to kind of dig deeper and see which pairs of groups are statistically distinguishable. So we already have an idea of that by looking at the previous data. We'll kind of delve into that a little bit deeper, see how we can do that. So again, we're looking at luteinizing hormone levels for 3 groups of women, and the one-way ANOVA reported a very small p-value. So we knew that there was some kind of difference there. And so, it would be quite rare if the values that we actually acquired were just due to chance alone. So we can know that we can safely kind of reject the null hypothesis at that point. But when you're looking at the family of comparisons, you kind of have to redefine what your significance level is going to be. So similar to the Bonferroni correction, you're going to be changing what your p-value you have to hit in order to achieve significance. And this is to avoid that multiple comparisons problem. So again, you're going to decrease your chance of getting a type 1 error, which would be a false positive. But by doing that, it's harder to achieve significance for those individual tests. And so you're more likely to get a type 2 error or a false negative, right? Because it's harder to achieve that significance level, more likely to accept the null hypothesis when it may not actually be true, right? And what's the best way to deal with type 2 errors? That's right, you increase your sample size, right? Okay, so again, when you're looking at just one comparison, you essentially have a 5% chance of just random sampling causing a difference between your whatever your means that you're comparing there. And again, that's going to be an error rate that's per comparison. So that's the problem we run into, is if you apply that alpha of 0.05 to every single comparison, you kind of keep ramping up your chances of causing a type 1 error. But when you're doing a family of comparisons, that's where we have that per experiment or family-wise error rate. And so when you put in your values and kind of have the different comparisons that you're doing, you'll get a new p-value spit out that says, like, this is what you have to achieve in order to be statistically significant. So basically just redefining what that value is going to be. Lots of different ways to do it. One of them is going to be this Tukey's test. And basically is comparing every mean with every other mean, and then will include these confidence intervals. And then this will allow us to make conclusions about some of the statistical significance. So I'll show you an example of what those graphs look like in just a second. So the next figure is going to plot the 95% confidence interval for the difference between the mean and every other mean. So essentially you're looking at the difference in means between each group, and based on that you can get confidence intervals and a p-value that'll tell you whether or not you've achieved significance with those individual groups. So again, if you were looking here, this is going to be looking at the difference in the log of the luteinizing hormone on your x-axis. And you can notice here that now we're comparing each group to one another. So recreational versus elite, non-runners versus elite, and then non-runners versus recreational. And so by doing this, you're looking at the difference in the means. You can kind of see the confidence interval bars that are here. So if you were looking at this, so if you're just looking at the recreational versus elite, and because we're doing the difference in means, so we're subtracting one from the other, would you consider that first one to be significant?
Yeah.
Why? The big difference, you think? Because remember, those bars are the 95% confidence interval. Notice what it's crossing.
Crossing the 0 mark.
Crossing the 0 mark, right? Because anytime I'm subtracting means from one another, 0 is going to be my level, my area for significance, right? If I'm doing a proportion and I'm dividing one by the other, then at that point is where you're looking at 1 being your threshold for significance. So in here, in this case, because I'm just looking at the difference in the luteinizing hormone, the recreational versus elite, that difference is going to be non-significant, right? That makes sense to everyone? Crosses 0. Looking at the non-runners versus elite, what would you say about that?
Also crosses 0.
Yeah, also crosses 0. So even though it's kind of trending more towards being significant, it does not achieve significance, right? Because it crosses that 0 mark. And then looking at non-runners versus recreational, yeah, and you can probably make some kind of common sense inferences about that. You imagine, you know what's, especially if they look at their definitions for what's recreational versus elite versus non-runner. That could definitely be skewing your data one way or the other. If there's the way they define it, that recreational and elite are kind of more close together as far as how much they're running versus non-runners and recreational. You can make you can see how those differences could be seen there, right? And changes in luteinizing hormone. But essentially what we're saying is that the difference in the 95% confidence interval, or the difference in the means here, we're kind of redefining what we consider to be significant. And so kind of what this test is doing is also going to be increasing the size of the confidence interval, right? Because of the fact that we're doing these multiple comparisons, by increasing the size of that confidence interval, you're also going to be more likely to cross 0, and you end up having the test that's not significant, right? So the more narrow your confidence interval, the more likely you are to achieve that significance. But by increasing that size, because we know that there's inherently more risk for a type 1 error with doing multiple comparisons, this kind of helps to get rid of that. So essentially what we're just looking at here is what we saw in that graph, where you're looking at the differences in the means, and you can see that there's really only one that was considered to be statistically significant, and it's that non-runners versus recreational. You could also do the same as well if you actually did a ratio of the luteinizing hormones, those mean values. So here, if I were to do a comparison, so I were to say divide the non-runners by the recreational runners, now because I'm dividing values, what's my level for significance, my threshold? Yeah, it's going to be 1 at that point. So if the values cross 1, then at that point I know that the value would not be clinically significant. So in this case, if I was looking at the bottom two, non-runners versus elite and then recreational versus elite, you notice here that what does it cross? 1, right? So you consider those to be non-significant. The first one still retains that significance even though you're doing a ratio, right? The confidence intervals are still being widened, but that one is still able to show significance there. So again, we did the ANOVA to all 3 groups to say, yes, there is some sort of difference here, but now we're digging into the multiple comparisons to find out really which group it was that was significantly different than the other. So again, if a 95% confidence interval for the differences between 2 means includes 0, then we know that's not going to be statistically significant. And again, 2 of those turned out not to be. And then in the comparisons of the non-runners versus recreational is the only one that ended up retaining significance. And then the same thing can be said for the ratios, but just if the value crosses 1, then or the confidence interval crosses 1, then it's not going to be significant. Okay, so again, the main thing that you're seeing here is that 5% significance level, that alpha of 0.05, is basically being applied to the entire set or the family of comparisons. So again, that's why we end up seeing the confidence intervals start to widen out, because again, we're saying that if I do all of these comparisons, there really should only be a 5% chance that random sampling produces a statistically significant result, right? Because that's going to be my threshold, that 5% for the entire set of comparisons. So as you might imagine, if I were to do, say, 10 comparisons instead of just 3, how do you think it's going to widen my confidence intervals or narrow it further? Probably getting even wider, right? Because again, you're trying to give yourself more leeway there to not make a type 1 error. So again, your results inherently get more or get less sure about the actual true values of those means as you start to increase the number of comparisons you have in order to make sure you're not going to get a type 1 error on accident. So again, just that alpha level that you need to hit for each comparison is going to go down as you increase the number of comparisons that you have. So again, just to look at this as well, this is the mean differences in the luteinizing hormone, and you can see that even though yes, the first one hit alpha of 0.05, that's all well and good, but because we're going to be doing a smaller alpha level for each of those comparisons, it still retains significance even down to a level of 0.01. So again, that's still pretty good, still pretty significant. That one, we can definitely say that that's the one difference in means between the groups that made the ANOVA positive in the first place, right? So now we did the ANOVA, showed it was positive, and now we've identified which group it was that actually showed the difference, which comparison showed the difference. So you can kind of take away saying that, okay, well, based on this, we can say there's really not a big difference in luteinizing hormone between non-runners and recreational runners, at least in this sample, but we can say that between non-runners and recreational, yes, there is a difference in luteinizing hormone. Now, what clinical significance that makes, I have no idea, but something they wanted to study. So again, multiple comparisons tests are going to account for these multiple comparisons. Obviously, the tests account for multiple comparisons by making the confidence interval apply to the entire family of confidence intervals, so just widening those out. And so, given certain assumptions that there's a 95% chance that all of the confidence intervals include the true population mean, that would allow us to say that only 5% chance that one or more of the intervals do not include the population value. And so just by random chance, you might find something that would be statistically significant. So just know this is allowing us to have less chance of making a type 1 error when doing these multiple comparisons. So with more groups, you're going to see that the confidence interval between means becomes wider. So as an example, if I had 3 groups with 3 possible pairwise comparisons of means versus 5 groups, you would have 10 possible comparisons of means, right? So as you increase the number of groups, you're going to have more comparisons you can make between them. And so that requires making the confidence intervals wider in order to make sure you're not going to have a type 1 error on accident. So multiple comparison tests using data from all groups, even when comparing 2. The one-way ANOVA is based on the assumption that all the data is going to be sampled from populations with the same standard deviation, even if the means differ from one another. Right. So again, by having similar sample sizes, that helps to achieve similar standard deviations. So you can kind of go and working with that assumption. And again, by making those assumptions, and again, this is a parametric test we're working with, we're assuming that we're doing normally distributed data, that this is going to give our test more power to actually find a difference if there really is one there. We'll see when we're dealing with non-parametric tests that those are typically less powered and to find a difference, and so you're less likely to make a type 1 error with those tests anyway, but we'll talk about those a little bit later. Okay, so you can just imagine here the number of pairwise comparisons as your number of groups go up. So it's certainly kind of an exponential increase as you increase the number of groups. So again, you hopefully don't have too many groups in your research study, because otherwise it's going to be very, very hard to find significance there to avoid a type 1 error. Just another graph kind of showing the same thing. As your groups go up, the number of pairwise comparisons go up exponentially. So again, when we're doing these multiple comparisons, they're accounting for intertwined comparisons, and that the multiple comparison tests can declare the difference between pairs of means to be statistically significant, but they do not actually compute out an exact p-value here. So again, these are really just telling us what the actual value of p that we would have to achieve is, and then you run the test yourself in order to determine whether or not you achieve significance. Okay. So that's it for ANOVAs and 2-way ANOVAs and 1-way ANOVAs and all that good stuff. Now we're going to look at non-parametric methods, which is referring, oh yes.
Sorry. So the alpha values that you determine are a priori before doing these tests, and you split them evenly between the comparisons?
Yeah, so if you already know what kind of groups and comparisons, because ideally when you're going into a research type setting, you want to know specifically this is the outcomes I'm looking for. These are the groups I'm going to be testing, and so based on that, you already know kind of going in what pairwise comparisons you're going to have to make. You already know what kind of outcomes you're looking for, so you can kind of set all that stuff up a priori and say, okay, well I'm going to set my alpha level for the family-wise comparisons of 0.05. And then based on the number of pairwise comparisons and doing the 2 keys test and all that kind of stuff, it will allow you to determine what that new p-value you need to achieve is for each of those comparisons, right? So it's just the computer system will spit that out and kind of tell you what you need to achieve to hit those. Yep. Mm-hmm. All right. So when I say non-parametric tests, what does that mean to you guys? Non-normally distributed data, right? So this is non-Gaussian data we're going to be working with now. And if you remember, we talked about Gaussian data, normal distributed data. We worked with means very frequently because again, and when you're working with normally distributed data, you don't really have a ton of outliers that are affecting your data, because we said means are very sensitive to outliers, right? They can affect your mean pretty significantly. So if you're working with non-parametric data, or data that's non-normally distributed, you are making less assumptions about the actual distribution. So you're going to see the outliers are not really going to have much of an effect here, because we're more dealing with medians. And you'll actually be seeing that we're running these tests are going to be more by basically by ranking the values by a certain way, and then or ranking them by the actual value itself from high to low, and then running tests based on that. So we're going to see that there's going to be an alternative, a non-parametric version of the t-test we're going to see. And so keep those in mind. Keep those, when you see those tests, know that, okay, this is the non-parametric version of a t-test from comparing two means together, right? So keep in mind how we're going to use these tests as we go forward. Okay, so again, non-parametric tests are going to be based on ranks, so they make no assumption about the population distribution. And so if you'd imagine, because I'm not making these assumptions, these tests are, in general, more difficult to achieve significance with, because I'm not saying that, yes, this is normally distributed data. It's normally harder in order to achieve statistical significance. Okay, that makes my data less likely to make a type 1 error and makes it more robust. Meaning that if I actually show a true difference here, I can be very confident that there actually is a true difference between whatever it is I'm comparing. So sometimes, frequently, if you don't know if your data is normally distributed or not, you can just run non-parametric tests, and if you see a difference, you can be pretty sure that yes, there is a true difference there, right? That's kind of the assumptions we're going with here. Again, they're more commonly, they work by ignoring the actual data values and instead just analyzing the ranks of the values from high to low. So again, unpaired t-test, ANOVA, paired test assumes a Gaussian distribution that can be defined by the parameters, and thus are parametric. Right? So that's where we get kind of that term from. But with non-parametric tests, we're making no assumptions about the distribution of the populations. Outliers are really not going to have much of an effect here to influence these. So simple non-parametric test rank values from low to high and analyze those ranks, ignoring the actual values themselves. In this way, it ensures the test will not be affected by outliers, does not assume any particular distribution. So that's kind of the key points there to remember about your non-parametric test. So if I was going to compare two unpaired groups, so if I had a parametric data and I was using two unpaired groups, what kind of test would you use? An unpaired t-test, that's correct. So in this case, if I want to use this with non-parametric data, now I'm going to use what we call a Mann-Whitney test, or Mann-Whitney U-test. Now you see a lot of these tests are going to be more named after the statisticians who developed them, so you can blame them, not me. But a Mann-Whitney U-test or Mann-Whitney test is going to be for two unpaired groups that I want to compare together. So it's very similar to an unpaired t-test, right? And these are going to be independent samples that I'm comparing when doing this, okay? So Mann-Whitney is a non-parametric test used to compare two unpaired groups and to compute a p-value. This works by basically you rank all of the values without actually paying attention to which of the two groups the values come from. So again, we're going to look at the rat and the bladder data in just a second. And basically it'll sum the ranks in each group, calculate the mean rank of each group, and then basically do some calculations to come up with a p-value from there. So just know that it's really doing with the ranks. It doesn't actually have anything to do with the values that you're having there. It just looks at the ranks in the different groups. And so here when they did the p-value, ended up coming up with 0.0061, showing there was a statistically significant difference between the values of the ranks basically of the old rats versus the young rats. Again, the samples here need to be randomly sampled and are independent, but again, we're not at this point making any assumption about their distribution, so we don't need them to be normally distributed. So here, we're comparing the old and the young rats together. You can see here how basically just by ranking the values, notice you can have multiple values that can be the same rank. So if you notice, there's a couple values that were the same. They kind of just get lined up side by side there. If you were to use two paired groups, so again, if you're using parametric data, you'd be using a paired t-test. In this case, though, if you were to use two paired groups, you'd use the Wilcoxon matched pairs sign rank test. So if you see Wilcoxon matched pairs test, this is going to be for paired data that is, you're comparing the two groups, but they happen to be paired, but non-parametric. So again, if you were looking at the null hypothesis, you say there's no difference between the two groups, but here we can get a p-value that tells us whether or not these paired data are statistically significantly different. And again, I'm not going to go super in depth, but just know that they're more looking at the ranks of the data rather than looking at specifically the values. And again, here they're accounting for that variability or the interperson variability that can happen. So that's why it takes into account for the paired groups there. And if we were looking at a p-value here in this situation, you get 0.0413. So that would end up being statistically significant at that point. Again, we're assuming the data is randomly selected, and and independent, but again, the pairs, the group is paired together. And again, we're not making any assumption about the Gaussian distribution. This is why it's a non-parametric test. So again, on a test question, it might come up like, okay, here's this clinical scenario, here's how this research questions are going to be done, which type of test would be most appropriate for this? So again, if I said I'm using a non-normally distributed sample, or I've done a normality test and I find that the data is not from a Gaussian distribution, and I'm doing two paired groups, which test would be best to compare the means between these two? And you say Wilcoxon match pairs rank sign test, right? So those would be important things to note, and we'll cover this in the review as well. Okay, so the other thing you run into issues with, especially why you might want to use non-parametric tests versus parametric tests, is if you're dealing with very small sample sizes. You run into some issues. So again, with a Gaussian population, if you're using a non-parametric test, it can be a little misleading, because if the problem with this is you may not have enough power to actually show a true difference if it's there. So you can run the issue running a type 2 error with some regularity. Because again, if I'm using a Gaussian population but I use a non-parametric test on it, I decrease my chance for making a type 1 error. The data is more robust, but with very small sample sizes, it's hard to show significance. So that can be kind of problematic. But with larger sample sizes, you're okay to go. So even if you're not sure if the data is normally distributed or not, with a large sample size, it really is not going to have much of a problem. You still should be able to show significance pretty regularly. On the other hand, if I were to use a non-Gaussian distribution and I were to apply parametric tests to it, that would increase my chances of making a type 1 error. And so, especially with small sample sizes, parametric tests are not robust enough to those violations of the Gaussian distribution. So I'm more likely to make type 1 errors at that point. However, if you have very, very large sample sizes, because as you get larger sample populations, you're kind of more closely getting to a Gaussian distribution, hopefully, you're going to see there's less problem with this. But again, make sure that the researchers, when you're reading the medical literature, that they're at least delineating what type of test they're using and why they're using, or at least be able to tease out why they're using non-parametric tests if they're using that, or if they're using parametric tests. Like, they've at least done some thought to it. And usually that'll be in the methods section when you read that. And then if you're really not sure what type of population you're dealing with, really you should start with normality tests to tell you whether or not you're pulling from a Gaussian distribution or not. Again, you may not be able to find much data if you have really small sample sizes, say less than 30 samples, but with larger samples that can be useful to tell you whether or not you should really be using parametric tests or not. Okay, so next we'll talk about sensitivity, specificity, and receiver operator characteristic curves, or the ROC curves. Okay, so when we're talking about sensitivity and specificity, you guys probably already have an idea of what this means. But the accuracy of a diagnostic test is usually quantified by the sensitivity and specificity, right? So sensitivity is that fraction of all those with the disease who get a positive test result, right? So that's your ability to really pick up those true positives, right? And then the specificity is the fraction of those without the disease who get a negative result. So you have to be able to kind of tune out the noise. The sensitivity is more like the signal, and then you're looking at specificity being the noise compared to that. And you want to make sure that if patients do not have the disease, your test reflects that, right? Because you don't want to accidentally tell someone they have HIV or something like that when they really don't. Okay, so then you can look at the predictive value of a test. So there's ways you can calculate both the positive and the negative predictive values for these tests based on their sensitivity and specificity. And so basically what these are telling us is that if the test is positive, what is the chance that the patient actually has the disease? So you can figure that out from the sensitivity and specificity. And then conversely, if the test is negative, what is the chance that the patient really doesn't have the disease? Right? And so we talked about this when we were talking about Bayesian statistics back in the first lecture, but we'll kind of cover this again now. But basically, the answers are going to be quantified by the positive predictive value and the negative predictive value. So those values are very important for knowing when you're looking at tests to see, just how good it is to actually pick up patients who do have the disease, and if it says it's negative, how actually true that it's negative. And so results are going to be based on the characteristics of the test and the prevalence of the disease in the population being studied. So you remember when we looked at, say a test that was 99% sensitive, the number of false positives you get changed pretty significantly when looking at a population that was routinely healthy and had very low incidence of HIV versus IV drug users, who the incidence was much, much higher. You had a much lower false positive rate in that group because your incidence of HIV is already higher to begin with. Okay, so you need to kind of know what your prevalence of the disease in the population is before going in. Okay. So. Good. How are you? Fantastic. We planned that out weeks in advance. I knew you guys would be kind of tired, so. Yep.
We planned that out.
Yeah, absolutely. Anywho, now that everyone's blood pressure is back where it should be. So essentially what we're going to be looking at when we're doing these tests and looking for positive predictive value and negative predictive values, essentially you're just looking at whether or not the disease state is present or not. And then you can look at to see the decision of the test, whether it came back as abnormal or it came back as a normal test result. And so again, doing the math here, you can figure out whether or not how sensitive and how specific your test is going to be.
How are these different from like reliability and validity of the test?
You're going to see that you guys know like the bullseye analogy. Right, so you can have something that is very reliable and very reproducible that can produce the same value every time, but it may not actually be accurate, right? So it could be very consistent, but it may not be accurate. And precise, exactly. Yeah. So the precision can be really good, but you may not have the actual validity of the actual test. On the other hand, you can have things that are not very precise, but could be somewhat accurate. So you have kind of more scattershot around the actual bullseye itself. But something that's reliable and precise, and very valid is going to be basically dead on in that bullseye. So I don't have that graph here, but that's basically what you'll kind of get to. I think we talk about that in the epidemiology section. Yep. So this is more just saying that whether or not the patient has the disease, how well this test is actually going to show a correct result or not. So one of the ways that you can kind of look at a test and show a curve that kind of show you how you trade off sensitivity and specificity, because the problem is that as I try to raise the sensitivity of a test, the specificity is going to end up going down at a certain point, right? So I'm going to end up getting more kind of abnormal results. And so every test is going to have a trade-off. And so these curves, these receiver operator characteristic curves, are very useful for kind of showing us this. And so your threshold can be set to have high sensitivity or high specificity, but very infrequently can you really have both. And so you can see these curves kind of show a trade-off between the two, and I'll show you what these look like in just a second. So to make sense of this, basically you see on your y-axis you have the sensitivity of the test, which sensitivity is what?
Picking up positives.
Yeah, so if the patient truly has the disease, that the test is going to come back positive. So you can see here your sensitivity being ranging anywhere between 0 to 100%. And then on your x-axis, you're going to be looking at 100% minus your specificity. So basically saying that as your test becomes more sensitive, your specificity is going to end up going down, right? And so you can generate these curves for lots of different tests to end up showing you kind of what the trade-off is between the two, and see basically, I don't see these reported too frequently, but sometimes if there's like a new test being devised, or if they are looking at new markers for disease state. So for instance, one of the problems we run into in toxicology is trying to identify patients with acetaminophen overdose who are going to develop severe hepatic damage. Sometimes you don't notice that for 24, 36 hours. And so one of the things they're looking at now is looking at certain protein adducts from the liver, and showing that if you can measure levels of this, how sensitive and specific is it for showing that these patients are going to have hepatic injuries. And so you can generate curves like this to show you kind of the trade-off between as you start to increase sensitivity, how does the specificity start to drop off, and you're going to get more false positives, right? So essentially that's what these curves are really showing you when you're looking at these. Okay, so again, interpreting these clinical laboratory tests requires combining what you know about the clinical context and what you've learned from the lab test itself. So again, when we're using that Bayesian logic, we're kind of going in with some pre-existing knowledge and then applying the new knowledge that we have, the new data that we have, in order to make an interpretation. So in these cases, you already know what the disease incidence is going into the environment, so you know what type of patient population you're dealing with, you know what the disease incidence is for that group, or the prevalence is for that group, and then you now have this new data coming back from this lab result to try to tell you whether or not something is abnormal or not. So again, we're going to be looking at basically the probability versus odds of these tests. So again, the likelihood of these tests being positive or negative can be expressed as either probability or odds. And so essentially what we're seeing here is that the probability that an event will occur is the fraction of times you can expect to see that occur in many trials. So again, this is very similar to what we saw with like relative risk versus odds ratios. But essentially, the probability is going to be a fraction that always ranges from 0 to 1, and any probability can be expressed as odds. Because again, we said you can just flip that over by doing your basically your probability divided by your 1 minus your probability would end up giving you the odds. And then odds, we know that it does not have to be between 0 and 1, can range all the way up to infinity basically. But again, when you're doing these proportions, know that when you're doing p-values and things like that, 1's going to be your level for significance here. So and then any odds again can be expressed as a probability. You can just do the math to figure those out. So one thing we're going to be looking at is the likelihood ratio. So this is going to be the probability of obtaining a positive result in a patient with the disease divided by the probability of obtaining a positive result in a patient without the disease. So essentially, to get the likelihood ratio, you end up getting the sensitivity divided by 1 minus the specificity, and that will give you the likelihood ratio there. And then looking at the Bayes as an equation, you can start to do post-test odds and pre-test odds basically. So what you end up seeing is that your pre-test odds is going to be kind of the incidence of the disease in your patient population that you already know going into it. And then you can generate these post-test odds to kind of give you an idea of how likely it is that if your result comes back positive, that the patient actually has the disease, right? So we said that as your incidence increases, as your pre-test chance increases, that usually means you're going to have less false positives in general, just because more of the patients actually have the disease state. So post-test odds are the odds that a patient has the disease, taking into account both the test results and your prior knowledge about the patient, and just the pre-test odds are the ones determined by the information you know before running the test. And so you just calculate that by doing your pre-test odds times your likelihood ratio, and that's also going to equal your pre-test odds times your sensitivity divided by 1 minus specificity. So this is how you get your post-test odds that tell you that if you get a positive result, this is the likelihood that you're actually going to get your patient really has the disease state. Okay, and then finally we're going to look at some stuff on sample size. Might actually be able to finish this. That'd be nice. Okay, so many experiments and clinical trials are run with too few subjects. Why do you think that is?
Really hard to find.
The hard to find patients, yep, right? I can only place so many Craigslist ads. Well,
You're exposing them to something that they may not like.
sure, yeah, so depending on what my experiment is, people may not want to, if I tried running all these snake bite experiments and people just for some reason didn't want to join in. I don't know why. It could be a cost issue, certainly. It could be just a very infrequent disease state. So lots of different reasons why studies are underpowered. As you might imagine as students, when you guys run your own studies, how likely are you to have a nice double-blind randomized controlled trial with 1,000 subjects? No, you're going to have like maybe 20 patients you can look at for whatever it happens to be. So again, studies, a lot of things end up being underpowered. So in an underpowered study, you're unlikely to find those significant results because your ability to find a type 2, or your ability to make a type 2 error is going to be increased basically. So even if the treatment did substantially change the outcome, you wouldn't be able to find it anyway because you don't have the patients to actually show the difference. So there's a couple of different approaches to doing sample size. We kind of talked about some of these earlier on in the class, but you can do things kind of ad hoc. So this is going to be kind of more convenience than anything else, where you kind of collect, analyze some data. If confidence intervals are not really as narrow as you like, or the results aren't statistically significant, you say, well, I'll go out and collect some more data and reanalyze and see what happens. You think this is pretty valid? Nah, no, not really, because you don't want to just do analysis until you find the right results that make your study look good, right? Because that's not good science. So we don't want to do that. You can do conventional, and this is where you do your power calculation. So basically, you choose a sample size based on the type of observed change you're expecting to see, based on your beta level, and then based on your ability to, so basically you calculate your sample size, come up with that, and then you're going to collect the data and then analyze, and you don't make any adjustments based on that. And if you didn't find a difference, then you conclude that, well, I couldn't reject the null hypothesis. It could have been due to the study being underpowered, but based on my power calculation, it seems likely or unlikely, whatever it happens to be. And then sometimes you'll have adaptive trials where actually we'll see interim analyses being performed while the trial is still proceeding, and then that helps you decide what you should do with the course of the study. So sometimes in very large trials, you may see this being done. Frequently, if the the intervention that you're doing is very significant, sometimes they'll actually stop trials early because they already have all the results they need to show that, hey, every patient needs to be taking this intervention or everyone should be taken off this intervention. So very frequently you'll see that actually lead to shortening of a trial. So remember that our confidence interval depends on the sample size. So as that increases, we're going to see a drop in our confidence interval. And so again, by stating the desired width of the confidence interval, the number of subjects needed can be calculated. And this kind of goes back to your power calculations when you're deciding before you even start the study. So, and again, 4 questions really need to be answered to determine how many values are needed to obtain statistical significance. So again, what's your significance level? So what's your alpha? How much power do you need? So again, in order to determine how big of an effect size you want to show, that determines how much power you're going to need to do that. And then what is really the contact? So you also have to look at kind of feasibility for being able to find those type of patients you want to involve in your study. So, any questions on that? All right, so we got through that stuff. We have, I think, section 9, and then we have the review, and then so we'll cover that next class. And then I believe we'll have our workshop. So I've told a couple of you guys about it, but essentially what we're going to do is I'm going to divide up the class into groups. I know group work is probably your favorite, right? For the introverts out there. And so I've found some studies, and what we're going to do is basically I'm going to assign your groups a study, and then we'll have a list of questions we're going to look at. So we're going to do things like, what's the independent and dependent variables here? What are, did the study do a power calculation? What is the type of study they did? Is this, what were the results they found? Were they clinically significant? Were they clinically significant? We're going to look at all kinds of answers like that, and we'll do some classroom presentations. So, yes, any question?
For the exam, are you going to use the examples in your PowerPoints, like the HIV one, the experimental study, or are you just going to give us new?
I have made up quite a few exampls, so it won't be specifically, but the concepts are all the same, right?
Okay.
Yeah, so, especially for test questions where it's like, I give these 2 groups of patients, these independent groups of patients a new treatment for hypertension, and the results came back as a mean difference of X with a p-value of this or confidence intervals of this, and then I'll ask you to make conclusions about that study, and so you have to kind of pick out the true conclusion out of the group of 4. And I'll give you some examples during the review of that. If we don't get through all of section 9 at the next class, I will post the review, and of course if you guys have any questions we can talk about them during the workshop as well. That work out? All right, thanks, and I will see you guys next time.